All right, so today we're going to be using concepts from information theory to optimize our key bindings in Emacs. If you don't know what that is yet, don't worry. I'm going to give an intro to information theory as part of this video. But the TLDR is that we're going to view our keystrokes in Emacs as information sent over a channel. And then we're going to calculate the entropy of my hands, create a Huffman encoding, and then we're going to use that encoding to see if I can come up with more efficient key bindings for myself. So information theory was discovered in the 1940s when Claude Shannon was working at Bell Labs to come up with a more efficient way to send messages over the telegraph. You see, the telegraph was an ancient way of sending messages way back before the telephone, and it worked like this. If you had a message you wanted to send, you would encode each of the letters in the message as a sequence of dots and dashes, and then you would send that sequence of dots and dashes over the wire. On the other end, someone would receive your sequence of dots and dashes and use it to decode the original message. Now, there are many different ways to encode letters as sequences of dots and dashes. You're probably familiar with things like ASCII encoding, but people figured out very quickly that if they used shorter sequences for the most common letters and longer sequences for the most unusual letters, on average, they'd be able to send their messages faster. So Claude Shannon sat down and he thought about this, and he wanted to know what is the best encoding and how much does it cost on average to send a message over the wire. To get an intuition for this, let's take a look at a simple encoding where every character uses a sequence that's the same length. If you have 10 bits, then you can encode 2 to the 10th different symbols, which you can see either by using binary notation or by using combinatorics, since there are 2 choices for each bit. Going the other way, if you want to encode 2 to the 10 different symbols, you'll need to use at least 10 bits, log 2 of 2 to the 10th. So more generally, if you want to encode k different symbols, you need at least log 2 of k bits to do so. Now, this is only for when you use a fixed length encoding for each symbol. So what happens if we use our little tricks and include shorter encodings for more common symbols and longer encodings for less common symbols? I won't prove all of the math behind it, maybe a good topic for another video. But what Claude Shannon figured out is the best way to do this is to use an encoding length that's proportionate to the probability that the signal occurs. So more specifically, if the probability of seeing a particular symbol is p, then the encoding length for that symbol should be approximately log 1 over p. Remember, p is a number between 0 and 1. So 1 over p is large for low probability events and close to 1 for high probability events. If you use this optimal encoding for each symbol, then the average number of bits you need to send over the wire is the sum of the probability each symbol occurs times the number of bits you need to encode that symbol. In our analogy, the emacs commands are the symbols that we want to communicate to the editor. Our key bindings are a way we encode that information to quickly enter the commands on our keyboard. Some commands take only 1 key press, or in our analogy 1 bit. Some commands take 2 key presses, and some commands take even more. What we want to do here is we want to choose an encoding or choose a set of key bindings for our editor so that we can communicate the same commands in the smallest number of key presses. So as a brief overview, what we're going to be doing is adding a keylogger to my emacs, figuring out the probability that I enter each emacs command, and then calculating a Huffman encoding so that the number of key presses I need is approximately the optimal value. To start out, we're going to need to collect some data. I added a keylogger to my Emacs config that records the current time, major mode, and keys pressed for every Emacs command that I enter. I couldn't find a package that logged everything that I wanted, so I actually wrote my own. But this implementation is loosely based on keylogger.l. I left this running for over 2 months, and I wound up with a text file that was over 100 megabytes. Today we're going to look at the data, and we're going to sit down and figure out what happened. I'll be using Clojure because it's the language I like the most, but the analysis that we're going to be doing isn't too complicated, so any language implementation will do here. Before anything else, I need to take this file and parse it from a CSV. The parser returns each element as a Clojure list, so I'm just going to quickly parse it into a map for easier access. Now the first thing that I really want to know is how often do I use each key command. So I'm just going to grab the frequencies of each command name and quickly look at some of the output here. But what I really want is the key commands that I use the most. So let's go ahead and let's sort by the number of times each command was seen. So now if I go ahead and I run this, I can see the command that I use most often is the self-insert command, which makes sense because that's literally just typing characters into a buffer. This empty string that I don't really understand. Then there's next line and previous line, which is basically just going up and down in a document. Kind of funny that these are almost exactly the same number. And these 2 commands that I use to turn on and off God mode, which is basically just an Emacs package that gives you a Vim style command mode. Something that's going to be kind of tricky for us here is that when a key sequence is bound to an anonymous function, our little logger just outputs a text representation of the function, which, as you can see here, is pretty hard to understand and follow. But if we have to guess what one of these are, we're just going to do our best. I'm actually really enjoying looking through these, just, for like entertainment. So I'm going to go ahead and show off one more page of results. You can let me know if you think your commands will look anything like mine do. All right, now on to the main event. We're going to convert these frequencies into a probability distribution, and then we're going to calculate the entropy of my emacs commands. Before we start, I'm just going to remove self-insert character and the empty string from our analysis, because I think it'll make the data harder to analyze. I'm also going to remove the next 3 commands, 2 of which correspond to mouse movement, and 1 of which is isearch printing car, which is sort of like a self-insert. Next, I just want to count the number of key command presses left in our dataset. And then, in order to get the probability that I'll enter a particular command, I would just do the number of times I see that command divided by the total number of commands entered. Now I just need to get the probabilities for every command in my dataset, and I can finally compute the entropy of the commands I enter into the Emacs editor. Now what this is saying, and this is really interesting, is that in order to send all of the commands that I send to the Emacs editor, I need to communicate an average of 6.5 bits of information per command. On average, I need to type something that's 6.5 bits long. Now, we're making a few assumptions here, like that I enter my commands in a random order, and that I'll be able to memorize and follow the optimal encoding. But in theory, it should cost me 6.5 bits. But what does that mean in real terms? Well, a standard keyboard has 26 letter keys and 26 other keys available for use. I'm going to assume that we're inside of God mode's action mode, so all keys are available without modifiers. And for the keys that do use modifiers, I'm going to treat them as 2 separate characters. Now we have a really simple model of the world. We have 52 different keys, and they each represent 1 symbol that we can send over the wire. We can go in reverse to get the number of bits you can encode with 52 different symbols, which, as we saw earlier, is log 2 of 52, or about 5.7. What this means is that if we have an optimal encoding, we can use an average of 1 key press, 1 single key press, per Emacs command, but we're not done cooking. You see, information theory tells us not just how good the optimal encoding is, but it also tells us how to get there. For this video, we're going to be using the Python library da-Huffman for our implementation of Huffman encoding. So going back to the project, I'm just going to import this library and call it on our list of frequencies. Unfortunately, the library returns the encoding in binary notation rather than keystrokes, so we need to do some extra work to convert the binary encodings into key commands. Basically, I did this by assigning each symbol to a binary value, and then replacing the binary values in the code with the corresponding symbol. So for example, 00000 followed by 00001 would be encoded as the key commands AB. In this way, every sequence of 5 or fewer binary symbols is encoded as a single key press. Since 52 is not an even power of 2, there are also some symbols of length 6. This approach loses a small amount of information, but it's guaranteed to be valid because it maintains the invariant that no encoding can be a prefix of another encoding. Alright, so now let's take a moment to look through these. I can see that common key commands like end of line, new line, and save buffer are represented as a single key press. And then I can also see that more rarely used commands are given more complicated sequences of keys. But as you can already see, there's a really obvious problem here. These key bindings don't make any fucking sense. Do you think I'm going to memorize the sequence 2JDQ for a command that I use 1 time? The standard Emacs key bindings are chosen to be short, but they're also chosen to be mnemonic. Control B stands for backwards character. Control F stands for forward character. Control S stands for search. The list goes on. Encoding commands as sequences of bits, we produced an efficient encoding, but it doesn't provide any value because it loses all of the semantic information of what the key command actually does. So now it's time to take our lessons from information theory and apply them so that we can decrease the amount that we have to type, but not increase the amount that we have to memorize. You see, information theory provides us with one more key piece of information. The length of a particular symbol should be approximately log 1 over the probability of that symbol occurring. This lets us find, in a mathematically precise way, how far our current key bindings are from the optimal ones. To compute this, we also need the length of the current key bindings that we actually use. I did log this inside of my logger, but it turns out that the internals of God mode mangled the way that my key sequences were logged. So I had to get the list of my currently active key bindings by running describe bindings inside of closure mode and then parsing the output. Then, for each command, I computed the optimal length of the key binding for that command. So, under the ideal encoding, how many key presses it should take to enter. I compared it to the actual length of the command. So, the number of key presses that it takes for me to enter that command under my current key bindings. Now, we can go ahead and compute the difference and figure out how far the length of our current key binding is from the ideal value. So now I'm just going to run this, and I'm going to sort by the commands with the largest difference. As you can see, this shows us the commands that we have where the key bindings are too long. These are the commands that we use constantly, but take a tremendous amount of effort to do so. I'm looking through this list, and it's absolutely wild. Like forward word, backward word, cider jack in. Every time I see one of these commands, I'm like, God damn it, like obviously I should fix this. Intuitively, I know what this list is. These are the same commands that annoy the shit out of me every day. Conversely, we can also sort by the commands that have the most negative difference. These are the commands that have a very short key sequence, but that we don't use very often. So for example, by default, Ctrl-Z is bound to suspend frame, which is basically the same as clicking the yellow minus to minimize the window. And I pretty much never do this, except on accident. And then I'm, annoyed that the window is minimized. What this list shows us is what commands we can unbind from their current key bindings. Taken together, these two lists tell us exactly what we need to change and how to change it. Specifically, we need to unbind the key bindings in the bad list, and then reassign them to key bindings in the good list. So for example, I can unbind Ctrl-Z from suspend frame, and then rebind it to save buffer, a command that I use much more frequently. We can keep most of our current key bindings, but rebind all of the worst offenders, so that we can happily use emacs with the smallest amount of typing. All of the code for this video is freely available on GitHub, link in the description. So you're welcome to try running this analysis on your own config, and see if you get any useful results. If you do run this for yourself, I'm super curious what happened. So if you have any results you want to share, definitely feel free to reach out or respond in the comments down below. Now, there's a lot of other things that I wanted to try as part of this video, but I didn't get to because I thought it would make the format too long. I think the ideas in this video have really interesting implications for general purpose UI design and HCI. And I would love to design a website that uses the principles of information theory, along with a lot of logging and analytics, to determine how menu items are laid out on the main page, and how nesting levels or multi-step menus are organized. I also made a lot of approximations during the course of this video. One of the biggest being that I did not consider the optimal way to assign key bindings to a multi-step sequence of commands. This is super important in taking discrete symbols to their information theoretic limits, and also intuitively, I think it will represent things that should be emacs commands. So key sequences that I use frequently that are doing something and could be represented by a higher level concept. I'm also planning to repackage a lot of the code in this video into an easy to use library with a nice user interface. So if you don't know anything about information theory, you can just run this and see what key bindings you need to change. And I'll add all the code for that into the GitHub link that's already in the description. Anyway, if you made it this far, give the video a like, subscribe to the channel, and I'll see you in the next one. I also want to thank you guys for helping me reach 1,000 subscribers. I know it's kind of dumb, but it's truly the motivation I need to keep this channel going. Anyway, thanks so much for watching, and I'll see you in the next one.